project. The title is relation between ionic conductivity and functional group differentiation in METHYLCELLULOSE LiTFSI and polymer electrolytes. For the background of study, increasing demand for a portable electronic device, electrical vehicle, and renewable energy storage has increased the safer and efficient electrolyte. Conventional liquid electrolyte provide a high ionic conductivity, but they suffer from a leakage, volatility, and flammability. While gel polymer electrolyte attract attention because they combine the advantage of solid and liquid electrolyte by providing a high ionic conductivity and a safer alternative. For the problem statement, MC-based polymer electrolyte has a relative low ionic conductivity due to the semi-crystalline structure. And secondly is LiTFSI and DS are expected enhance ionic conductivity, and mechanism responsible for this improvement remain unclear. And lastly is the relation between the ionic conductivity and functional interaction of MC, LiTFSI, and DS has not fully understood. The objective of this research, first one is to establish the ideal formulation parameters for MC, LiTFSI, DS, gel polymer electrolyte system that maximize the ionic conductivity performance. Secondly, to analyze the interaction of functional group of MC, LiTFSI, DS regarding the effect on ionic conductivity performance in gel polymer electrolyte system. And lastly, to investigate the relationship between structure and polymer interaction, including hydrogen bonding and ion dipole interaction with the ion transport mechanism in MC, LiTFSI, DS, gel polymer electrolyte. For this literature review, MC acts as a polymer host that contains hydroxyl lithium group that facilitate the hydrogen bonding and lithium ion coordination. Secondly, LiTFSI acts as a lithium salt by supplying mobile lithium ion and ion coordination and ion production, and also can exhibit the high ionic conductivity, good ionic dissociation, and excellent electrochemical stability. And DS act as a plasticizer by reducing the crystallinity of the polymer matrix and increase the polymer chain flexibility and promotes the dissociation of lithium ions. Next, for the research methodology, the step for sample preparation start with the added MC into the DMSO by continuous stirring at 65 degrees Celsius and stir until homogeneous solution was obtained. After that, LiTFSI was added slowly to the MC solution by continuous stirring at 65 degrees Celsius and also stir until homogeneous solution was obtained. After that, DS was added with different various concentration to the MC LiTFSI solution and stirring and continuous stirring and until homogeneous and GPE was formed. Here is the table composition for MC LiTFSI DS gel polymer electrolyte system. This is a designation sample. This is a designation of one sample, which is DS gel that contains 30 gram of DMSO, 1 gram of MC, and 0.2 gram of LiTFSI with 10% of DS. Followed by DS30, DS30, and DS40. The DS was varied with 20, 30, and 48% of DS. Here the characterization of sample. Firstly, electroimpedance spectroscopy (EIS) technique was used to determine the bulk resistance of the polymer electrolyte by using the frequency spectrum. From the measured bulk resistance, we can identify the ionic conductivity by using this formula. From the formula, we know that the ionic conductivity was inversely proportional to the bulk resistance, and that can determine the lower but resistant has a higher ionic conductivity. Secondly, for Fourier transform infrared spectroscopy, FTIR was investigated the functional group by analyzing the absorption peak at specific wave, and the frequency used which is 4,000 until 600 per centimeter with 2 revolution and 16 scans. For the result discussion, here is a result discussion for ionic conductivity but resistance studies. The figure shows the linkage plot for all the samples that contain partial semicircle at high frequency region and inclined spike at lower frequency region. Which is the partial semicircle represent a bulk resistance at polymer electrolytes, and inclined spike represent the ion diffusion and electrolyte interface. As we can see, 28% of ES has a lower bulk resistance, which is 370.670. This is because 28% of ES was added can improve the ion dissociation and reduce the resistance. And also the lower bulk resistance can make the lithium ion move easier through the polymer electrolytes. Next, result and discussion for ionic conductivity studies. This figure shows the ionic conductivity versus DS concentration for all the samples. As you can see, the ionic conductivity was increased from the 1.87 exponent -4, which is at the 10% of DS, to the 3.49 exponent -4 at 28% of DS. However, when DS was increased to the 30 and 48%, the ionic conductivity was increased to the 3.27 at 38% of DS, and also decreased to the 2.97 exponent -4 at the 48%. As we know, the DS concentration up to 28% reach a highest value of ionic conductivity, which is 3.49 exponent -4 Siemens per centimeter. This is because DS can enhance the polymer chain flexibility and promoting lithium ion mobility. And after DS was added to the 30 and 48%, the excessiveness of DS promotes the ion dissociation and can reduce the efficiency of lithium ion transport. So we can know the optimal DS concentration at the 28% of DS samples. Here, this is the result and discussion for FTIR analysis. This figure shows the FTIR spectra for the raw material that I used in this study, which is pure MC, pure ELECTROLYTES, and pure DS. For the pure MC, show the characteristic functional group at OH. Functional group OH at OH 2092, HOH at 1640, and CO functional group at 1060. And the pure ELECTROLYTES exhibit the characteristic SO2 at 1350, SMS at 1050, and CF3 vibration band CF3 vibration band at 1060. Lastly, for the pure DS, display a broad OH at 3250 and CH at 1940 and CO vibration at 1050. This characteristic being used as a reference spectra for polymer electrode and identify the change after the addition of DS was added. This is the figure that FTIR spectra for pure NC, pure LiTFSI, and pure DS with different DS concentration. The FTIR spectra confirm that the successful incorporate of MC, LiTFSI, and DS in gel polymer electrolyte, increasing of DS in trade. increasing of DES concentration, slight peak and bordering and peak shifting are observed at OH region and CO region. This is because stronger molecular interaction of MC, L-LiTFSI and DS. As you can see, no new absorption band were observed, indicating the physical interaction rather than the new chemical bonding was formed. Here is the result and discussion for FTIR basis. This is the FTIR spectra for OH region and CH region. For the OH bending vibration, when DS was added to the 20, 30 and 48%, the border become more visible after DS was increased. This is because the stronger hydrogen bond interaction between hydroxide of MC and the hydrogen bond donor and hydrogen bond acceptor of DS. For the CH deformation bending vibration, as the DS increased, there's only minor change in peak shape and intensity was seen. This is because the addition of DS modified the molecular arrangement of the polymer change, but not changing the chemical structure. Next, FTIR spectra for CO region and COC region. The CO sensing vibrations at slight peak shifting bordering to the higher wave number. The peak bordering observed after the DS concentration was increased indicates the interaction of lithium ion with oxygen atom and enhance the ion transport. Next, for COC sensing vibration show a slight peak shifting after DS was increased. This is because DS indicate the increased polymerization flexibility due to the plasticizing effect of DS and provide more pathway for lithium ion movement and improve ion mobility. Next, to summarize the correlation between ionic conductivity and structural properties of MC, L-LiTFSI, DS, and polymer electrolytes. As we know, the lowest spark resistance obtained from a linkage plot at DS20, which is 20% of DS samples, and exhibit the high ionic conductivity, which is 3.49 exponent -4 siemens per centimeter, and also RP can replace the ionic conductivity. For structural properties, FTIR spectra, peak shifting and peak bordering were increasing the DS concentration and indicating the stronger molecular interaction of MC, L-LiTFSI, DS in each samples. For the conclusion, the DS is successful in enhance the ionic conductivity and structural properties of MC, L-LiTFSI, DS, gel polymer electrolytes. DS MP, which is 28% of DS sample, exhibit the high ionic conductivity, which is 3.49 exponent -4 siemens per centimeter, indicates the optimum DS concentration. The optimal plasticizing effect of DS enhance the polymer chain flexibility and segmental motion of the lithium ion motion and lithium ion dissociation and ion migration. And also, FTIR confirm the hydrogen bond ion dipole interaction with increase the amorphous structure and supported EIS result. And lastly, MC-LiTFSI-DS gel polymer electrolyte show the potential for solid state energy storage device such as lithium ion battery and supercapacitor. For the recommendation for future study, investigate the DS concentration closer to the optimum value, which is 20% of DS, such as 15, 18 and 22% sample to determine the exact optimum concentration for maximum ionic conductivity. Secondly, perform addition characterization such as SRT to analyze the crystallity and amorphous nature for the polymer electrolyte. Next, can evaluate the different lithium salts such as compared to the L-LiTFSI such as LiPFSI, LiPF6, LiCiO4,
Thank you so much. Dr. Sarah, good presentation. Present